Okie dokie, let's get started, chemists. So today's lecture, this week will be cut short, so today will be the only day you'll be with me in lecture this week. We also don't have any labs this week, but do double check the due dates for your post labs from last lab. Some of them have been extended, but not all of them. So do double check those due dates for that post lab to ensure that you turn things in on time for that last LLT lab. All right, so we're going to, excuse me, wow, thank you. Thank you, I've been holding that one in for a while. Chapter 6, electronic structure of atoms. Actually, before I get started, I wanted to let you all know, for those of you planning ahead, the next review session and the next midterm, midterm 3, the review session is actually going to be next Friday at 5:30. I couldn't get this room for Thursday, so it's going to be on Friday instead. I haven't written it yet, so I will post that information on our Carmen page soon. But yeah, just keep that in mind, earmark that in your calendar that it's going to be next Friday. And I will, as always, record it and have it available on Zoom. All right. So we just finished up our thermochemistry chapter. So we talked about energy of chemical reactions. And so, you know, I've taught this course a couple times, and I always thought that, you know, chapter 5 to chapter 6 was a very big transition, basically a 180 in terms of concepts, where we went from energy of chemical reaction, stoichiometry, to now let's talk about the atom again. Let's talk about electrons, kind of like we already did in chapter 2. But I think these two chapters have actually a lot in common. So let's review this kind of reaction and energy scheme for a reaction you've probably seen before, right? Let's think about when we take fuel, react it with oxygen, and we get CO2 and water. What kind of reaction is that? If we squint our eyes, what does that look like? A combustion reaction. Do we know the sign of delta H for these combustion reactions? Negative, yes, these are exothermic reactions, all right? So here I have an energy diagram of this very reaction. Notice how our reactants start at a higher energy, a higher potential energy than our products, where after the course of the reaction, we end up in a lower energy state. This results in the release of energy. So notice how we go downhill overall. And this is related to that negative delta H value, all right? So this is like a combustion reaction. You take fuel, react it with oxygen, get CO2 and water. But let me ask you this. As humans, you know, we eat food, we breathe oxygen. What are our products then? If we eat food, breathe oxygen, what do we exhale? Or like what are our products in this case? See, carbon dioxide, right? We inhale oxygen, we exhale CO2, and we actually exhale moisture as well, H2O. So the idea when we burn calories really is a combustion reaction, all right? Where we put fuel in our body, we breathe oxygen, we use that energy in an exothermic reaction and release CO2 and H2O, all right? So we're no different than a burning fire. So that's what humans do. We do like the forward reaction here. But what about plants? What do plants eat? CO2, yeah. And what else do plants eat? Water, yeah. And what do plants make? Oxygen, and they make fuels like sugars and stuff, right? So really what plants do is they do this exact reaction, but backwards, yeah. But notice if we do this reaction backwards, is it still an exothermic process? No, it is actually an endothermic process. So plants go this way, all right? Plants go this way. It is now an endothermic process. It requires energy for plants to turn CO2 and water into oxygen and other fuel sources, all right? So where do plants get that energy? The sun, yes, the sun. So what happens is that sunlight comes in, right, to energize, push this reaction forward to get it up this hill. So these two chapters actually are in fact related, because what we're going to actually talk about is light a lot in this chapter, and how light interacts with matter. Really confused scientists on how light interacts with matter and models to describe it. So that's what we're going to talk about in this chapter and how light is very important with how it interacts with matter. All right, so these are the things we're going to talk about. All right, so we're going to talk about electrons in a very, very in-depth way, much deeper than what we talked about in chapter 2. What I like about this chapter is it explains a lot of like the really funny memes that we see on the internet and stuff. Sometimes we share funny memes thinking that we understand the meaning behind them, but I really, I'm pushing you to, do you really understand the meaning behind like the Schrodinger cats comic and other things like that? But what we'll see in this chapter is atoms. We've talked about the different subatomic particles of an atom. We got protons, neutrons, and electrons. We're going to really focus on electrons. And what we're going to learn here is that electrons are really weird, all right? They're really weird. They have very bizarre behavior that really confused scientists, and a new type of mathematics had to come about in order to explain the behavior of electrons. All right, this is what we call quantum mechanics. Things get really, really complicated when things get small. And so that's basically the basis behind all of these different funny comics. I think I found them all on physics memes subreddit, all these different comics. And also, just like a couple years ago, I rewatched the entire like Marvel Universe thing. And what I noticed in one of the movies like Ant-Man, all right, and if you've watched, excuse me, Endgame and the whole like premise of the Marvel Universe is that once they introduced that superhero Ant-Man, they were able to like unlock time travel, right? Sorry for ruining it for people who's watched the Marvel thing. Okay, all right. Yeah, so with Ant-Man, all right, when they introduced this character, I was really surprised where they basically showed, hey, when Ant-Man got super, super small, right, time became really weird. And there's kind of some truth in that, that yes, electrons are very, very small. And on that small level, we basically have different physics that comes up. And so, that was kind of the ability for like Endgame and like a kind of somewhat happy ending at the end when they unlocked time travel. So there is some relevance to what we're going to learn into real life and movies. All right, so let's talk about electrons and light. Okay, so in order to understand more about electrons and electronic structure of atoms, we got to talk about some of the definitions of light. Why do we have to talk about light? It's because we can't see electrons. We can't see them. We're able to, like deflect them with magnets and stuff because they're negatively charged, but we can't actually see them. But we can see light. So let's define some things about light. Light is just simply a wave. And so we can use wave characteristics to describe them, such as wavelength and frequency. They have different units here. Wavelength is simply a length. So you will see units like meter, nanometer, or angstrom. Angstrom is another unit. It simply means times 10 to the negative 10 meters. All right, just like nanometers was times 10 to the negative 9, angstrom is just a little bit smaller. This is kind of on the realm of where the size of atoms live. So angstrom is a common unit there as well. So wavelength is simply just a size, where frequency is a little bit different when we talk about a wave. It's how many peaks pass a certain point per second. So if we think of like a ray of light as this wave, I like to think of it as this squiggly noodle that's kind of propagating itself through space. If we measure peak to peak, that's its wavelength. Or it can be trough to trough, it's the same length. But if we think about this wiggly noodle moving through space at the speed of light, the frequency in which every time a peak passes a certain point, that is its frequency. So we see that wavelength and frequency are actually inversely proportional. They're related by the speed of light. Here, the speed of light in a vacuum is a constant, 3 times 10 to the 8 meters per second. And so what we can say is that the speed of light is equal to the wavelength of a specific wave times its frequency. And so we can see how those units kind of cancel out. Wavelength, when it's in meters, and we multiply it by its frequency, which is 1/seconds, we do get meters per second, which is the velocity or speed of light that we have here. So yeah, frequency has that unit of 1/second. So it's like a per second. It's just how many of those peaks are passing through a point per second. 1/second, sometimes you'll see it stylized as s⁻⁻1 or the unit of hertz as well. They all mean the same thing. All right, so let's just do some calculations to make sure that we understand how wavelength and frequency are related. They are inversely proportional, all right? That shorter the wavelength, larger the frequency. Longer the wavelength, smaller that frequency. So let's do this. Dr. N's favorite laser color has a wavelength of 490 nanometers. What is its frequency in hertz or (10⁻⁻1? So what we need to know here, we have our equation that relates speed of light, frequency, and wavelength. Speed of light is a constant. It's simply 3.00 times 10 to the 8 meters per second. So we need to make sure that our frequency and wavelength match those units. We are given what? We are given wavelength, but we want to calculate frequency here. Okay, that's what we're trying to calculate. So when we put in the wavelength value into this equation and solve for frequency, let's just rearrange this equation. So we're trying to solve for frequency, so it is equal to speed of light over wavelength. I want to make sure that wavelength matches and cancels with the appropriate units in speed of light. Speed of light is in meters per second, so what should the unit of wavelength be in? Can we keep it in nanometers? Nope, we got to convert it to meters. Yeah, so notice that this is 490 nanometers, so we can simply rewrite this as 490 times 10 to the -9 meters, because that is what a nanometer is, all right? So that is our wavelength. I'm going to put that at the bottom there, so 490 times 10 to the -9 meters is my wavelength, and so we get an answer. Do I have it in the corner there? Yes, 6.1 times 10 to the +14. And here we can see those units cancel. Meters cancels. So we're left with a per second on the numerator, and that is the same as a hertz, right? 2 sig figs probably, because 490 has 2 sig figs. All right, and it's all multiplication. All right, so there's one. Let's do one more here. So one shade of visible violet light has this frequency. What is its wavelength? So we're just kind of working backwards here. I give you frequency. I want you to calculate wavelength. So we're given this, calculate that. So I'm going to rearrange this equation just so it's we're calculating for wavelength. Wavelength equals speed of light over frequency. So let's put in those numbers. So 3 times 10 to the 8 meters per second over its frequency. I gave this to you. There's no manipulation that we have to do. The units will cancel beautifully here. 7.3 times 10 to the 14 hertz, or 1/second, same thing. And so you can see, yes, the seconds cancel. So when we solve for wavelength here, the value that you calculate is 4.10 times 10 to the -7. That's what your calculator says. But what's the unit of this? Meters, yes. Meters, because the per seconds cancel, leaving you with the meter there. But let's convert this into a nanometer. We see this is typical for visible light. So let's remind ourselves that 1 times 10 to the -9 meters is 1 nanometer. And so this is equal to 410 nanometers. All right, there we go. All right, so do understand the relationship between frequency and wavelength and how it's related to the speed of light. They're inversely proportional. You're oftentimes going to see light in light wavelengths in the unit of nanometers, just because that's the typical unit we use for visible light. But do understand that you have to convert that to meters in order to use these equations. All right, so that is light. So let's talk about light in terms of matter, all right? So we need to talk about kind of like the weird phenomena that happens with light, some of its weird behaviors. And so when scientists were studying light, they came across some weird observations. You know, as a scientist, oftentimes we like to make equations to match the observations that we see. And so something interesting happens with this phenomenon called black body radiation. Black body radiation is a phenomenon we see if we heat something up really, really hot. Oftentimes we see that object glow. So like, let's think about, you know, if you take a metal skewer and you put it into a campfire for a long time and you take it out and you observe it, what does it look like when you take out a really hot metal skewer? It glows red. Oftentimes we say, if something's really hot, we say, oh, it is red hot, meaning it is so hot, it is glowing red. We can think of the same idea of like the coils on our ovens or on our stoves. When they're on, you can see, oh, they're glowing red. All right, so what you're actually observing here is black body radiation. Really hot things glow red. And so what scientists did was they tried to make these equations to explain the observations we would see. But there was a problem. Every calculation and every equation that they made ended up in disaster. It would always end up as, oh, if you heat something up really, really hot, it would actually emit ultraviolet radiation, which isn't what we actually see. Typically, we see red light or white light, not ultraviolet. And so it came to Max Planck finally came up with a solution and determined that, oh, light has to only transfer a minimum amount of energy. There's this minimum amount of energy that light possesses. And he called this minimum energy a photon. So basically, you can think of light as not only a wave, but a single packet of energy being transferred to an object that we call a photon. And once Max Planck introduced the idea of this singular packet of light, the photon, then all of the equations started to make sense. All of the equations started to match exactly what our observations saw. He got a Nobel Prize for basically the discovery of, not the discovery, but the understanding of light and its relevance to a photon. So what we're saying here is that light is quantized. We can have a minimum amount of energy that is transferred. We can count single photons of light. And we can calculate the energy of each of those photons, and it's related to not only its wavelength, but also its frequency. So here we see that the energy of a photon, which is basically just a single packet of light, is equal to Planck's constant, which is given right here. You will always be given this value, times its frequency, right? So what we see here is that light with very high frequencies also have high amounts of energy. Or we can rewrite this in terms of wavelength as well, because we have this wavelength frequency equation. We can rewrite that the energy of a photon is equal to Planck's constant, speed of light over wavelength. So those are both the same equation. Use whichever one you have. If you're given frequency, use the frequency equation. If you're given wavelength, use the wavelength equation. All right? So this equation tells us the energy of one photon of light. So now we have light that has different properties. It has a wavelength, it has a frequency, and now light has an energy. All right, so that brings us to the electromagnetic spectrum, where we can bring all of these topics together, all right? We interact with different types of light. These types of light have different energies, they have different wavelengths, and they have different frequencies. So you do need to know the general order of these different types of radiation. Like, you need to know that a microwave has less energy than visible light. That would be an example, all right? And so with all of these relationships, what we see is that everything over here, cosmic rays, X-rays, these are high energy light sources versus the different sources over here, like microwave, radio waves. These are all very low energies. So once you have that general trend of energy, then you can apply the trends of the relationship between energy, frequency, and wavelengths. So because of these two equations that we introduced earlier, all of these things are related to one another. Once you know that, okay, X-rays are high energy, radio waves are low energy, we can say things that have high energy also have high frequencies. So that means X-rays have what? High or low frequencies? High frequencies, yes. But at the same time, if we have high energy, high frequency, it also means short wavelength, all right? So an X-ray has what kind of wavelength? Long or short? Short, all right? So you don't have to memorize the order of all of these things in terms of energy, frequency, and wavelength. You don't have to memorize all of them. Just memorize one. Just understand the order in energy, and then relate frequency and wavelength to those as well. So what we see here is that microwaves and radio waves have very long wavelengths and very small frequencies because their energy is very, very low. Right? All of those things are synonyms with one another. All right. Okay, cool. So do know the general trend there. Notice how visible light is kind of just this small, tiny sliver here, where purple or violet is on the high energy side. Notice that this visible light color scheme that you see here, the purple and the violet is on the side of the ultraviolet, while the red part of our visible light is up against what part? Infrared. So that kind of tells you the energy scheme there as well. Scientists are not super creative, all right? So we see that does red light have high or low energy compared to that whole visible spectrum region? Low energy. But what about its wavelength? Long wavelength, yes. While purple has high energy, short wavelengths. Perfect. All right, good. All right, so that's the general electromagnetic spectrum. All right, so let's put energy of light and electrons together. So we'll talk about some more Nobel Prizes here, all right? This Nobel Prize comes from Einstein, all right? So typically when we think of Einstein, we think of like his theory of relativity, Einstein's equations, things like that. But I think it's funny that he didn't win a Nobel Prize in any of those things, the things that he's most well known for, like relativity. He actually won the Nobel Prize in the phenomena of the photoelectric effect. So this photoelectric effect really highlights the importance of light acting like a photon. All right, that there's this minimum amount of energy that light can deliver to an object. So what this photoelectric effect was he took a light source and he would shine it on a metal surface, right? And what he noticed is that when that light had a certain amount of energy, when it had a certain wavelength, then electrons would start to be emitted from the surface, right? But if we were below a certain energy threshold, no electrons would be ejected from the surface. Right? So the idea here is when the energy of the incoming photon was greater than what we call the work function of the metal, electrons were emitted. But when the energy of the photons was lower than the work function of the metal, then no electrons were emitted. So let's actually look at a simulation here showing you it because it's hard to explain. Let's just do the experiment right here. All right, so what I have here is my light source. You can see it right here. I can change the intensity of the light source, and we'll kind of look and see what does that mean. And we can also change the wavelength of the light source as well. So when we change the wavelength of the light source, we're actually changing the energy of the light as well. So we have this metal surface. Right, so I'm going to increase the intensity here. So do you see any electrons being emitted from the surface when I shine this light on it right now? Nope, no electrons. So what we need to do, what Einstein did, was he slowly increased the energy of the incoming light source until we would see electrons being emitted. So if I want to increase the energy of this light source, should I make the wavelength longer or shorter? Shorter. So let's make it shorter. So right now I'm at about 600. There's 570, 540. Any electrons yet? Nope. So let's see, when will there it goes. All right, so right there. So now at around 525 nanometers, we definitely see electrons being emitted from the surface of the metal, all right? But if we go back to 600, If we go back to 600, notice no more electrons. So electrons are only emitted once we are above that work function of the metal, which seems to be around 520 nanometers, all right? But let's think, what if we deliver higher energy photons? So 400, 300, 200. Are electrons still being ejected? Yes. And is anything changing about the electrons that are being ejected once I slowly increase the energy? So here are like kind of lower energy electrons, and then here are really high energy photons, sorry. Right, so we see that with very, very short wavelengths that the ejected electrons have a lot of kinetic energy being transferred here, and it's because of the leftover energy from that photon going towards increasing the kinetic energy of that ejected electron, all right? So let's just kind of go back to a normal thing. There we go. Okay, so that's a little bit more normal. All right, so here we see that electrons are still being ejected because we're above the energy, the work function of this piece of metal. So now let's look at intensity, all right? So right now my light source is basically as intense as it should be. How does intensity fit into this? So here we basically have like 100% intensity right now, but if I lower the intensity, what changes? Are electrons still being ejected? Are we sure? Just watch long enough. Yes, they are, but just less frequently. Yeah. So what we see here is that intensity is basically the rate at which photons are being ejected. So let me show you a different view. All right. So instead of like the beam of light, right now I'm showing you the light source as actual photons, like individual particles hitting that surface. And so what intensity is just the rate at which photons are basically being emitted from this light source. So right now this is a fairly low intensity, 14%. So let's look at a high intensity. Yeah, a ton more photons being shot at this metal surface. And so what we see is with more photons, more electrons are ejected. Right? So let's look at one more example. So let me go back down here. Right? So when we use orange light, so like 600 nanometer light, are electrons being ejected? No. Will changing the intensity at all force electrons to be ejected? No. Intensity is just related to the amount of photons being generated by our light source. The only way we can make electrons become ejected is by changing that wavelength, thus the energy of the incoming photons coming in. All right, so there we go. There's our demo. So maybe we can answer some questions now that are on this slide. All right, so the big idea here is that the energy of our single photon is related to its wavelength, all right? Where short wavelengths have large energy photons. And what we see is when the energy of the photon is above that of the work function of the metal, that is when electrons are ejected from that metal surface. So let's answer these questions. What happens when we increase that intensity of light? What we saw is that the number of photons of light increases, thus ejecting more electrons from the surface, but only if those photons had enough energy to begin with. If there wasn't enough energy of those photons, like if we used low energy red light, changing the intensity did nothing, right? It's only if we were already above the work function of that metal. All right, what if we use higher energy photons by changing or shortening that wavelength? We saw that the ejected electrons had greater kinetic energy, and this is due to the conservation of energy. The idea that if you're sending in a photon with lots and lots of energy, you know, some of that energy is going to go to ejecting an electron, but all of that leftover energy goes towards the kinetic energy of the electron. It goes towards increasing its velocity. All right, so that's the importance of this experiment, the idea that, hey, these photons also act as particles, because what we see is that for every one photon, it would only eject one electron if there was enough energy to unbind to basically eject that electron from the surface. So yeah, this experiment really highlights the particle properties of light. Light isn't just a wave, it's also a particle as well. And that's very important to our understanding of electronic structure coming up in a bit. All right, so let's do one more calculation with light and energy. All right, so if photons are particles, that means we should be able to count them like particles, all right? So like we can talk about the energy of one photon using this photon energy equation, or we can talk about the energy of a mole's worth of photons, which we can calculate here as well. So let's work through this question. So what is the energy of a single photon of UV light with this wavelength, 204 nanometers? Let's get this in joules. So we will use the energy of that photon equation. So notice that the energy of one photon is related to Planck's constant. Since I'm giving you wavelength here, all right, in nanometers, I'm going to use this version of this equation. So it's hc over wavelength. Notice that these are the same equation. I'm just replacing frequency with wavelength instead. Because we know that frequency is equal to speed of light over wavelength. So I'm going to use this version of the equation since I'm given wavelength, and we'll just go ahead and plug in those numbers. Speed of light, Planck's constant is given here, 6.626 times 10 to the negative 34 joule second. So it's like a joule times a second. Then we're going to multiply by speed of light, 3 times 10 to the 8 meters per second. And then we'll divide by that nanometer, but we can't keep it in nanometers. We should convert it into meters. So this is 204 times 10 to the negative 9 meters. All right, so let's check those units and make sure that we get an energy value out, all right? So we see meters cancels from speed of light and wavelength. And then we also see that seconds cancel. So we see that the leftover unit here is in fact a joule. And that's exactly what we want. We want to know the energy, the joule amount that is possessed in one photon, one packet of this 204 nanometer light. And so if you calculate that, you get that the energy of one photon, it's written down there, 9.7 times 10 to the negative 19 joules. That is the energy of one photon, all right? If I threw one ping pong ball at you, I would deliver that much energy. That's a tiny amount of energy. And so just like atoms, are we ever just interacting with one photon of light? No. So what we're going to do is scale up this number to a mole amount, all right? So in the next question, I'm asking you, what is the energy of 1 mole's worth of these photons instead? What we just calculated is the energy of 1 photon. I want what is the energy of a mole's worth of those photons. So the idea here is we're just going to change the unit, 9.74 times 10 to the negative 19 joules in 1 photon. I want instead what is the unit in kilojoules per mole. So we just have to change both units. We need to change joules to kilojoules. We can do that. And we needed to change 1 photon to a mole's worth of photons. We can do that using Avogadro's number. So let's change those units one at a time. Which one do you want to do first, the top one or the bottom one? Top, yes. All right, so let's change joule to kilojoules. That one's straightforward. There's 1,000 joules and 1 kilojoule. Perfect. So we got the top unit done. So now let's convert that bottom unit. I want to convert 1 photon into a mole's worth of photons. So we can use Avogadro's number. I want this to be in the unit of moles of photons. How many photons are in a mole's worth of photons? 6.022 times 10 to the 23 photons are in a mole's worth of photons. So notice how joules canceled. What else cancels? Photon also cancels. So what we're left with is the unit of kilojoules per mole of photons. And that's exactly what we want. And so what we get here, if you put this into your calculator, you get a very nice number that comes out in kilojoules per mole. So 587 kilojoules per mole. I really like that number because it's a nice whole number, like in the hundreds, versus the number 9.74 times 10 to the negative 19 joules. That's a really ugly number, but I do like the number 587. So oftentimes when we talk about light sources, you will oftentimes see the unit kilojoules per mole of photons to describe the energy of that light source. all right? But they're both describing the same type of light, 204 nanometer UV light. It's just different units to describe the same thing. All right, so that's light, right? We can talk about its wavelength, its frequency, and its energy. And all of these things will be important when talking about atoms. So let's remind ourselves the components of an atom. We talked about this in chapter 2. You know, we have protons, neutrons, and electrons. We're going to actually focus more on the electrons part of an atom, and that's what we call the electronic structure of an atom. We want to understand more about it because when we introduced those subatomic particles in chapter 2, we were able to go from Dalton's model to the plum pudding model to then Rutherford's model, all right? Where Rutherford's model knew that we had a very dense nucleus and we just had this diffuse, you know, cloud of electrons on the outside. We're going to really focus on how can we better describe that cloud of electrons on the outside. So right now we are here. So we're done with the plum pudding and all of that. We're going to move on to what the actual electronic structure of an atom is. This Bohr model, this is typically what you see when people show atoms. This is actually incorrect. All right, this is actually the true electronic structure of the atom, and I'll show you what these things mean. Lots of Nobel Prizes here, so the Schrodinger equation is the absolutely true explanation of a hydrogen atom. But the Bohr model does a pretty good job. We'll go into deep detail about the Bohr model. So what's going to help us in these last two sections of going into the true absolute current model of our atom is how does light interact with matter, right? We want to make sure that the observations that we see match the models that we have, all right? And so what a problem that came up was that the models we currently had did not properly explain some of the phenomena that we saw, specifically with line spectra of atoms. So when we think about light, usually we think about like white light, okay? White light, like in this room, is composed of the colors of the rainbow, right? Where it's actually a continuous spectrum of light, meaning that if you separated white light, you would see every single color of that rainbow represented, all right? It's versus what we would see, so this is white light. But when we would excite different elements, we would also see light emitted, but it was a different kind of light. It was not a continuous spectrum of light. What we saw instead were these discrete lines, right? And so these discrete lines were really important because our current models could not properly describe these lines. So let me show you some examples of line spectra. So let's turn down the lights. Turn down the lights. Okay, all right, so we got some line spectra here. So I have a couple samples here. So these different tubes are just filled with different elements, different gases, and what we're going to observe are the different line spectra of them. So here's this first one. This is helium. All right, so if we took a prism and tried to separate the light coming off of here, we would not see a continuous spectrum like we see in white lights. We would see these discrete lines, all right? So that's helium. Then I can show a different element. This is neon. So neon has a different set of lines. It's a different element. Another one. This one is argon. Ooh, argon. Ooh, yeah, it's a really dark purple. So here we see a different set of lines from argon, different color. Krypton. No, I don't know what colors. What color is that? It's like a light purple we see, yeah, for krypton. And then the last one I have here is xenon. Doo-doo. Yeah, it's a really, really light purple blue color, all right? So really into the UV, so we can barely see it with our human eyes. All right, so you might be looking at these and being like, oh, that's just like a neon sign. It is. A neon sign is essentially a gas discharge tube where we emit and see the different lines from the line spectra of those different elements. So the importance of this demo and these lines is that the current models we have, the Rutherford model, does not properly explain what's happening here. We need to make sure that the models that we have explains these different lights that come off with specific energies, these different lines that come off of these discharge tubes. So that new model does explain what's happening, and that is the Bohr model. All right, so the Bohr model is made up of 3 different postulates, basically 3 different assumptions, 3 different truths that help us explain the lights, the lines that we see off of the elements, different elements. All right, and so here is the first rule to Bohr's, the Bohr model. The first rule is that electrons can only orbit or reside in specific energy levels on a hydrogen atom, right? So really what, these models of the atom try to do is try to explain where are those electrons. In the Rutherford model, let me just go back real quick. The Rutherford model didn't really describe where those electrons are. They just said, oh, they're in this diffuse cloud, right? But what the Bohr model tries to do is put and explain where these electrons around our atom are. And that's what this first postulate says, is that we can only put electrons in certain radii around our nucleus. An analogy is these different energy levels, the different places we can have an electron on our atom is kind of like rungs on a ladder, all right? That in order for our electron to be stable, that electron can only be on a rung of a ladder. If you think about using a ladder, can you be stable and have your foot between like rungs 2 and 3? No, you can't. You have to be like either on rung 1, 2, 3, or 4, etc. And it's the same thing about an electron. It can only exist in these certain energy levels, right? And so what we see is that we can call these energy levels different things. The lowest energy level, N equals 1, we number these energy levels, 1 being the lowest, and increase in counting. We call that first energy level the ground state, and any higher energy levels the excited state, right? And so we can calculate the energy of any single energy level of a hydrogen atom if we wanted to. And what we see is that the energy is related to its energy level number. So N equals 1 is going to have the most negative potential energy, while if we increase to go to different excited states and increase the value of N, that energy for that specific level does go up. So this equation calculates the energy of one energy level, so N. Let's go into a little bit more detail of that here in this second slide, right? So details that we can't ignore about energy levels here. So if you look here on the left side of this slide, I have those energy levels written, but I want you to notice what are the energies of these different levels. So notice that there aren't actually any numbers here. It's just some numbers and a constant, the Rydberg constant. But what you see is that all of these energies for these different energy levels are negative values. Why are they negative values, these energy levels for an electron? So let's think about that. Remember, electrons, they're attracted to a positively charged nucleus. So if we have an electron and it's attracted to a nucleus that's positively charged, when we think about potential energy and the equation that describes potential energy, electrostatics, Q1 times Q2 over distance, when we have a oppositely charged particles, what kind of interaction is that? Do we call that repulsion or attraction? Attraction. So when we talk about attraction, that means we're looking at the bottom part of this graph. Remember, this bottom part of this graph are negative potential energies. Negative potential energies describe attractions. So that's why all of these values are negative, where the lowest, most stable ground state energy level is the most negative, but higher energy levels start to approach 0. So the second question, so now that explains why these energy levels are all negative values. It's because we're talking about attractions of the electron to the nucleus. So then the second question is, why aren't the energy levels evenly spaced? You know, I made the analogy that energy levels are like rungs on a ladder. You can only have electrons on specific rungs or on specific floors. Why do the rungs start to get closer and closer together the higher we go up? So notice that the first jump is the biggest, then it gets smaller, 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 smaller. Why does that happen? Well, if we look at this energy graph for like a typical attractions electrostatic energy, what we see is as the N value, our energy level increases, the distance from our electron, the distance our electron is from the nucleus gets larger and larger and larger. So when we look at this energy level, we see that as we change the distance of our electron from the nucleus, the largest change happens kind of when the electron is close to the nucleus. But once we get further and further and further away, notice how the change is less and less and less and less. So basically, this graph reflects how the energy changes in this graph. So notice how the change is less as steep as the further we get away from this nucleus, all right? So basically, yeah, this graph reflects the change of potential energy shown in this potential energy electrostatics graph as well, all right? So yeah, what we need to know for our hydrogen atom is that the energy levels are a negative potential energy, and they start to converge the higher in energy levels that you go up. So it's not equally spaced like a regular ladder. The rungs on the ladder get closer and closer and closer together the further you go up. So it's a really weird looking ladder, right? So those are some details that we just needed to talk about. All of this comes out of the equation as well if you were actually to calculate the energy of different energy levels. Okay, so that's the first postulate. Electrons can only be in certain energy levels. The second postulate is that electrons are only permitted in those certain energy states because that's where the electron is stable. What this second postulate is saying is that if an electron moves between different energy levels, then energy will be radiated. So the idea here, if we think about like an electron attracted to a nucleus, let's think about this. All right, so if I have an electron and I have a nucleus that's positively charged, there's attractions there, right? So what's stopping an electron from just crashing into the center of the positively charged nucleus? What's stopping the negative charge and the positive charge from just smashing together? Well, if that would happen, then all of our atoms in our universe would never be stable, right? So this is why we have to have the first postulate. If there were no stable energy levels on an atom, then our electrons would just go crashing into the nucleus and nothing would be stable. So the idea here is if there are no energy levels, if I pull an electron up and just drop it, it'll just go crashing down to the floor and not be stable. Versus if I have energy levels there, if I have rungs on a ladder present, if I pull an electron up and drop it, then it'll stay stable on one of those energy levels, right? So this postulate just says that you need to have those energy levels in order for an electron to be stable on an atom. If they weren't there, then the electron would just go smashing into the center of your positively charged nucleus. All right, so let's talk about the third postulate, which is kind of the most important one. And this one talks about how light interacts with our atoms, and it explains why we see the lights that we see, the different line spectra for these discharge tubes, right? And this is the third postulate, right? So we learned from the first and second postulates that electrons have to be in certain energy levels. So what the third postulate says is that light is involved, either emitted or absorbed, when an electron moves between energy levels, all right? So we can have an electron and it's stable in an energy level. It'll stay there indefinitely until it moves between energy levels. In order to do that, in order to go up rungs on a ladder or down rungs on a ladder, light is involved. Light is energy, all right? So what we see here is that the light that is involved, or the energy that's involved with these electron transitions, is related to the light of the photon, all right? So earlier we talked about the energy of one energy level. So what we see here is that when an electron moves up or down between two energy levels, this energy difference is related to the energy of the photon that is involved with that process, all right? So it's when the electron moves between energy levels, light is involved. Either it's emitted or it's absorbed. So this actually brings us back to chapter 5, us understanding what is the significance of energy being emitted or absorbed. So what we see here is that the energy of the photon is related to the energy change of the electron or the atom that it's making. But let's think about this. If a hydrogen atom absorbs light, all right? If it absorbs light, if it absorbs energy, what is the sign, the change of energy for that atom? Is it positive or negative if it's absorbing? Positive, all right? So that means the atom is gaining energy. That energy is going towards the atom. So what's going to happen is it forces your electron to jump up to a higher energy level, right? So when your atom absorbs light, that light contains energy. That energy forces an electron to jump up to a higher energy level, right? It jumps up to a higher energy level that's equal to the light that it absorbed. Remember, light is energy. And so that energy is transferred to your electron to make it jump, right? So that's what we have right here. If your hydrogen atom absorbs a photon, N increases for your electron jumps up higher. Or you can think, okay, the atom gains energy. Or you can think this is an endothermic process, that delta E of your atom is gaining energy. All of these things kind of mean the same thing, but what happens in the end is your electron jumps up, right? Versus the opposite. If your atom isn't absorbing light, it's emitting light. When does that happen? That happens when your electron falls, right? If your electron starts out at a higher energy level and falls to a lower energy level, right? That energy is converted into light energy, right? So here we see a hydrogen atom will emit a photon. What happens is your electron falls, the N value decreases, or you can think your atom loses energy, or this is an exothermic process, or delta E of your atom is negative, right? So what we see here, if we go, to this picture, this transition going from N to N1 to N equals 2 requires a certain amount of energy. So let's say if I tell you that like this transition requires 400 nanometer light to happen, if my electron falls from N equals 2 to N equals 1, can you tell me what is the wavelength of light that's emitted? It's 400, all right? So remember, the energy difference is related to the wavelength, the energy of the wavelength of light that's emitted. So whether you're going up or down, 400 nanometer light is still involved. You just have to think, is light being emitted or absorbed in this situation? So when we go up our energy level diagram, we see that light is absorbed, but when we go down, we see that light is emitted instead, all right? So this is how we get the different lines of our line spectra from our hydrogen atom. So notice if you look really closely, sorry you can't see very well, but there are 4 different lines on this hydrogen atom, all right? So this red line versus this purple line have different amounts of energy. The red line, think about the color red. Does that have high energy or low energy? Low energy, yes. Long wavelength, small amount of energy. Purple, on the other hand, has large energy, short wavelength. So we see that these lines result in different transitions of a electron on our hydrogen atom, right? Because what we see here is that the transitions between these different states, they can differ, all right? So we see like the energy difference between these two states, between these two are different. So we see different energies of light can be emitted from those different transitions. That's how we get the different colors off of our atoms when we show their line spectra of their discharge tubes. And so this is how the Bohr model is able to explain phenomena like this, where we have different lines coming from different elements. Different elements have different electronic structures. The light is only emitted when electrons are changing or making transitions between different energy levels. All right, so let's do some examples, put it all together. All right, so here I give you an electronic structure for a hydrogen atom. And I want you to match these different transitions with these different lights. So remember, when electrons undergo energy level transitions, that is when light is involved. So match these different light sources. So what I'm showing you are waves to the different transitions. So my guiding question or my hint here is, okay, how do these waves differ? They have different wavelengths. So what I'm going to do is order them in terms of high energy and low energy. So which of these, I guess, has the highest amount of energy, A, B, or C? Or 1, 2, or 3, sorry. 1. This one has high energy. Why does it have high energy? Short wavelength. It's because it has a short wavelength. Okay? Therefore, 3, wave 3 is going to have very low energy because it has a very long wavelength. And then 2 is in the middle. All right, so can we match these different waves with these different transitions? Which wave will be emitted or involved with transition A? A represents what kind of transition? A transition with a very small energy difference, energy change, or a very large energy change? Large. So what kind of photon should be released? A photon with a lot of energy. Yes, so what we see here is that transition A is going to be the high energy photon because look, this is a huge transition, right? Then therefore, wave 3 with the very low amount of energy is going to be which transition? C, yes. C, and then therefore the middle one, B, is B, right? So what we see here is that the amount that you drop is related to the energy difference. If you drop a very large amount, that's going to be a very high energy photon that's being released. Versus if you only drop a little bit, then that will result in a photon with a very small amount of energy, so a long wavelength. All right, following up question. In these examples, is light absorbed or emitted? What is it? Look at the direction of these arrows. All the arrows are going down, so our electrons are falling. So our atom is what? Gaining energy or losing energy? Losing energy, so light should be emitted. It should be emitted in this case, yep. All right, so let's do another one. This is a very common conceptual question, a common exam conceptual question, right? So here, which of these electronic transitions for a hydrogen atom corresponds to the emission of a photon with the shortest wavelength? I'm going to highlight the very important statements. Emission of a photon with the shortest wavelength. So my strategy here is I need to, like in this question, I gave you the energy level spacing. But in this one, we need to draw it ourselves, all right? So we have 4 different transitions between n equals 1 to n equals 4. So we need to draw an appropriately spaced energy level diagram, all right? So here is my n equals 1. Here is my n equals 2. Then they start to get closer, n equals 3, and then n equals 4. All right, so that's my crude hydrogen atom. Next, I want to draw these different transitions, right? So actually, even before I start drawing them, let's dissect what we're looking for. We're looking for emission of a photon. So what kind of transition are we looking for? Are we looking for a transition where the electron jumps or where it falls? Falls. So can't we eliminate half of them? Yeah, let's go ahead and eliminate half of them. Right, so we are looking for where the electron falls. So this first one, A, going from 1 to 4, that's a jump. Yeah, so that one's actually absorption. All right, so A is not correct because this is absorption. 2 to 3, that's also a jump. So that is absorption. So we can eliminate that. So we have 4 to 2 and 3 to 1. So it's one of those ones. So let's draw it. We have 4 to 2. So right here, this is 4 to 2. And then we have what? 3 to 1. 3 to 1. All right, so those are my two different options. But let's read the rest of the statement. So photon with the shortest wavelength. My strategy for, my tip for you is convert that into energy. So if I say short wavelength, that means what kind of energy? Big energy. Yeah, so we want the largest energy. So are we going to look for a small fall or a big fall? A really big fall. Yeah, so we want to look for a big fall. All right? So which one is that? Is that 4 to 2 or 3 to 1? It's 3 to 1. Yes, it's 3 to 1 is the bigger fall here. All right? So notice that I'm just looking at the magnitudes of these arrows. I see that the 3 to 1 is a lot larger than the 4 to 2 jump. But let me show you this. What if you didn't draw this energy level diagram correctly? What if you drew it like this? What if you just drew it like a ladder? Could you answer this question? Draw the transitions now. 4 to 2, 3 to 1. Are those arrows, or those falls are the exact same distance, right? But what's wrong with this picture? Are our energy levels actually spaced this way? They're not. So that's why starting this question with an appropriately spaced diagram is very, very important, right? So notice there's like a million ways I can ask questions based upon this, all right? Because I can ask emission of a photon with the shortest wavelength, or I could say absorption of a photon with the longest wavelength, or I could talk about frequency. There's tons of ways I can ask this question, but you need to understand that emission of a photon means that your electron falls. But if I ask you absorption of a photon, then that means your electron is doing what? It's jumping. And we have to relate to what does that have to do with energy. So if I say short wavelength, we're looking for a large energy gap. If we're looking at like a small frequency, we're looking for a small energy gap, for example. So different ways to ask basically the same question. I like questions like that because it's very conceptual and quite straightforward. Versus a question like this is a little bit more time consuming. I'm going to just go really quickly over this because this isn't a commonly asked question. But here I'm asking, what is the wavelength of a photon emitted in nanometers when the hydrogen atom undergoes this transition? So we're going from 4 to 2. All right, so we're actually just calculating what is the wavelength associated with this transition. When that electron falls, what kind of photon is emitted? That's what we're calculating. This isn't a common exam question just because it's very time consuming, but we can do it anyway. So we're going to use this equation. This equation will be given to you if you have to calculate wavelength of a electronic transition. But the idea here that you need to get behind is that you need to know that the change in the energy of your atom is equal to the energy of the photon that is emitted. So what we're going to do is calculate how is the energy of our atom changing. It has to do with how the energy levels are changing. So let's just go ahead and calculate that. Here our initial energy level is 4, and then we're going to 2. So when we plug in these numbers, we have 1, your final energy level squared. So this is 1 over 2 squared minus 1 over 4 squared. Is that right? Yeah. So then we have 1 over 4 minus 1 over 16, I think. I think that's what that is. Right? So let's just multiply all of that work out. Do I have that here? Let's do it. Okay. So we're going to multiply that. So we have negative 2.18 times 10 to the negative 18 joules. 1 over 4 minus 1 over 16 is equal to positive 0.1875. Right? So what we see here is that the energy change of our atom is equal to negative 4.087 times 10 to the negative 19 joules. All right? So our atom is losing a little bit of energy. right? So remember, don't let that negative sign mess with you. That negative sign just tells you which direction energy is going. So if our atom is losing energy, if our electron is falling, a photon is going to be involved how? Is it going to be absorbed into the atom or emitted? It's going to be emitted because our atom is losing energy. So what we're going to do is we're going to take the absolute value of this, and this is equal to the energy of the photon that is involved. Remember, the negative sign just means the direction energy is going. We can't calculate a negative wavelength. That makes no sense. We just want to use the absolute value, the magnitude of this energy change, and note that the negative sign means that that photon is being released, all right? So what we see here, and we've done calculations like this before, that the energy of our photon is equal to hc over wavelength, and we just calculated that it is equal to 4.087 times 10 to the negative 19 joules, right? So we want the wavelength. We know what Planck's constant is. We know what the speed of light is. So if you just rearrange some stuff, wavelength is equal to Planck's constant, so 6.626 times 10 to the negative 34 joule second. Speed of light, 3 times 10 to the 8 meters per second over that joule amount we just got, so 4.087 times 10 to the negative 19 joules. And so when you calculate this, you get the wavelength is 4.86 times 10 to the negative 7 meters, but I'm going to go ahead and convert that to nanometers. This is 486 nanometers, right? And this is the photon that is emitted. So the idea here is that the magnitude of your atom energy change, depending on how those levels are changing, is equal. That energy change is equal to the energy of the photon that is either absorbed or released, or absorbed or emitted. How do we know whether it's absorbed or emitted? It's whatever sign delta E atom is. If it's positive, then the photon is absorbed. If delta E atom is negative, then that photon is emitted instead. Just like we can think about energy being like light, or we can think about it as like heat, like in chapter 5, all right? Okay, so that's putting it all together, relating, the energy levels we just talked about with the Bohr model to the different lights of the line spectra that came from our atoms, and finally relating it back to wavelength and frequency that we talked about at the beginning of this chapter. All right, so why is this all important? Why does atomic structure matter, right? It matters because it's what brings beauty in our world. It's what makes us, colorful and diverse. Here's a question: why is grass green? Okay, why is grass green? It's not because grass absorbs green light. It's not because grass emits green light. It's actually because grass is green because grass contains energy levels that absorbs all visible light except green. All right, so therefore, when white light hits grass, it absorbs all of that light, but then reflects green light into our eyeballs, into our detectors, So if we think about, the different colors of skin that we have as chemists in this classroom, why are there different colors? It's because we have, all of us have different amounts of melanin in our skin. Melanin absorbs different amounts of visible light. So some of us just have a lot of melanin, some of us don't have a lot of melanin. That's how we get all these different beautiful colors. It's why I carry my rainbow bag, because I love light. I love how light interacts with electrons, that I buy this rainbow IKEA bag to remind me how much I like light. So this is why atomic structure matters. It's why we have a very beautiful and diverse world here. It's why we see all the different colors that we see, all right? Because colors is what makes the world beautiful. Even though I don't wear a lot of colors, I only ever wear green or black, but I do enjoy the beauty in the colors that I see around me. So that is why electronic structure matters. All right, so we got, 10 minutes? We gotta keep going. There's a lot to cover for chapters midterms 3 and 4, so we gotta keep going and talk about the wave nature of matter, all right? Let me just recap. We talked about light. We talked about light acting like a wave. You know, we have the wave properties of light. We have wavelength and frequency. Then we talked about light acting like a photon, like in the photoelectric effect. We could calculate the energy of a photon, right? So we talked about light earlier in the chapter behaving like both a wave and a particle. So what we're going to talk about is kind of just take a little bit of a jump there. You know, if we can say a wave like light is a particle, then why can't we say particles can be waves? Is that too much of a jump? Like if waves can be particles, can't particles be waves? Maybe. So that is basically what Louis de Broglie said in his PhD dissertation in France. At the time, it was like crazy and like unheard of. So much that like the chemistry department that he was in was like, no, we don't want you to go through with this. Go find another committee to support you. So this was a instance where de Broglie came up with this crazy idea, just saying, hey, if a wave can be a particle, maybe particles can be waves. He wrote his dissertation, and then sometime later, it was proved that, oh, he was actually right all along, all right? So that was kind of neat there. So he basically said that, you know, light can be a particle, right? Light can be a photon. So particles can also be waves as well. And so he came up with an equation, the de Broglie wavelength equation, that says that any object has a wavelength as long as it has mass and it's moving through space, all right? So we see this equation, wavelength, the de Broglie wavelength is equal to Planck's constant again, so it's the same constant we saw before, over its mass, the mass of that object, over its velocity. So that means any object in motion has a wavelength. So me just walking across this classroom, I have a wavelength. But where this is really important is electrons. Do electrons have mass? Are you sure? They have a tiny bit of mass, just a tiny bit, because remember that pinwheel experiment, right? Yes, it spun that pinwheel. They have velocities. They're whipping around your atom. So electrons, though it's a particle, they do have a wavelength. And so what we see here, based upon this equation, what kind of wavelengths do we get? When mass increases, your wavelength decreases. So objects with really large masses. I have a large mass. Do I have a big de Broglie wavelength or a small, short de Broglie wavelength? Very, very, very small, because my mass is so big. But an electron, on the other hand, it has mass, but its mass is so tiny. It's really, really small. So an electron actually has a very large de Broglie wavelength. So big that it actually starts to matter, all right? And that's the whole point in this next phase of understanding our electron and atomic structure is electrons actually have wave characteristics that we have to talk about, all right? And so in the end, he ended up being right. And so here's some examples. X-ray diffraction is taking light, and it's a wave property of light, all right? An X-ray is a type of light. You can send it through, you know, different diffraction patterns and get these patterns. That's a wave property of light. But what we see is that electrons can also diffract itself. So here's an example of electron diffraction, all right? Where we can take a beam of electrons, particles, and they too can diffract like a wave can, like light can. And diffraction, again, is a wave property where waves can either constructively or destructively interact with one another, either increasing its amplitude or decreasing it. So yeah, the diffraction patterns kind of came later and proved that de Broglie was right all along. All right, so let's do a quick calculation here. Let's calculate what is the wavelength of an electron moving with this speed. Here is the mass of an electron. So we're going to calculate its de Broglie wavelength. So wavelength equals Planck's constant, mass, velocity. Planck's constant's a constant. I gave you the mass of the electron, and I gave you its velocity. So we're just going to plug and chug these numbers together. So Planck's constant, 6.626 times 10 to the negative 34 joule second. Mass, 9.11 times 10 to the negative 31 kilograms. And then velocity, so almost 6, 5.97 times 10 to the 6 meters per second. So I'll remind you that what a joule is a kilogram meter squared over seconds squared. All right, and then we're multiplying that by a second here. So this whole unit looks like this. So if we cancel out our units, kilograms cancels, one of the seconds cancel, another one of the seconds cancel, and then one of the meters cancel. So what we are left with is in fact a meter, so a length. So yes, this is in fact wavelength. So if you do this calculation, you get 1.22 times 10 to the negative 10 meters is this electron's de Broglie wavelength. I'm going to just convert that into a different unit called an angstrom. So this times 10 to the negative 10 is the same as an angstrom. So 1.22 angstroms is the de Broglie wavelength of an electron. And so why we need to consider the de Broglie wavelength of electrons importantly on atoms is because 1.22 angstroms, that is about the size of an atom. So the idea here is that an electron, it is, orbiting our atom, but it also has a wavelength that is on the same magnitude, on the same order of the actual size of our atom itself. And that becomes very, very important in the next part of this chapter where we talked about the Schrodinger equation. So I want to take a moment and talk about, I've introduced two equations today that introduce wavelength, but they are different. So we just talked about this guy, the de Broglie wavelength, de Broglie, right? Here's our de Broglie wavelength equation. This equation relates an object in motion, has a wavelength, all right? An object in motion, how do I know? Because this equation has mass in it and it has velocity. So it's an object in motion. Versus, we looked at this equation earlier. This is the energy of our photon. All right? This is a different equation, but it also includes wavelength. But this is the wavelength of a photon. Is there any mass variable in that first equation? No, there's not. So do not confuse these two equations. If I give you wavelength, it doesn't mean you automatically use the de Broglie wavelength. You have to understand the context. If I'm talking about light, then you're going to use the first one. But if I'm talking about like an object in motion, you are going to use the de Broglie wavelength equation instead, right? Okay, so why is this all important? The wavelength of an electron. It's because with this idea that an electron has a wavelength, it kind of causes some issues in calculations. Because what we've noticed here is, when objects are big, they have very, very small de Broglie wavelengths, and we can essentially ignore them. But for an electron, its mass is already really, really small. Its de Broglie wavelength is actually quite big enough that it's bigger than the atom that it resides on, that we can't ignore its de Broglie wavelength. All right, so that's what Heisenberg did. All right, that Heisenberg started to consider, well, electrons have a wavelength. Let's consider them. All right, so the idea here with Heisenberg, he introduced what we call the uncertainty principle. And this is the basics behind quantum mechanics, is that when things are very, very small, we can't know anything for certain, all right? So how many of you have taken physics? Yes, many of you. Okay, so in physics, when objects are big, they have very small de Broglie wavelengths. So we can just ignore the wavelength component, all right? And that's basically what classical physics is. When objects are really big, we can know everything about an object in motion at any time. If I kick a football across the room, I know the football's position, I know its velocity, I know its momentum at every single moment while it's traversing the room. That's classical physics. What quantum mechanics says is actually we can't know everything about an object at the same time. And this is very important when things are very, very, very small, all right? So this is where we will pick up after fall break. I will show you Heisenberg's uncertainty principle and that we can't know anything for certain due to this. So have a great fall break. Do practice chapter 5. It'll be on midterm 3.